Hi, my name's Anna Harper. I'm going to tell you about our Short Landscape Decisions project, JEM, which stands for JULES Emulator of Ecosystem Services. This work was mostly done by Evan Baker at the University of Exeter, with lots of input from the rest of our project team. Land use decisions are complex for many reasons, partly because the land surface itself is complex and is comprised of several interacting systems. Land surface models attempt to represent some of these processes and systems and their interactions, such as vegetation growth, the carbon and water cycles, and surface energy exchanges. Land surface models are useful for predicting how the land will respond to changes outside what we see today, so they're good tools for answering the questions on this slide. We'd like to have the best models possible, but no model is perfect, so we'd also like to know about model uncertainty to help answer questions about how we use and manage the land. However, land surface models can be difficult to calibrate due to having lots of parameters, and they can take a long time to run depending on the resolution. So in our project, we use JULES, which is a land surface model that can predict the impacts of land use change on vegetation and soil carbon, net carbon uptake by the land, bioenergy crop production, soil, water, and runoff. We only had 6 months, so we chose to try to emulate one output of JULES, the gross primary productivity, as a proof of concept. We performed some initial evaluation of some applications of the emulator, and hopefully we learned some lessons that can be useful for future projects. I don't really have time to go through this slide, but if you don't know about emulators, you can come back to it. So a land surface model produces one output for a set of inputs. For example, JULES could predict GPP based from a set of parameters, climate data, soil properties, and land cover. An emulator is built from an ensemble of the original model that spans the plausible input space, so lots of model runs with varied parameters. In this project, we realized that we could simplify things because our version of JULES doesn't have interactions between grid cells. So instead of running JULES for the whole UK lots and lots of times, we just ran a subset of grid cells that were representative of the input space and had varied parameters. This turned out to be a very useful simplification because to run JULES for the entire UK would take about 24 hours per simulated decade with 72 processors at a 1 kilometer resolution. So once we have the emulator, we can predict outputs for all possible inputs. So this is an example of the emulated GPP for one day in June in 2002. This is really useful because generating this map only took about 20 minutes on a laptop. So now we could quickly analyze the impact of changes to climate or land cover on the GPP. And we could also easily extend this to look at other outputs from JULES, such as soil carbon, bioenergy crop production, or runoff, by building emulators of those outputs as well. Also, when the emulator is combined with observations, you can begin to rule out certain combinations of inputs, such as parameter combinations that give unrealistic results. And that's what we did here. This is an example of improvements to JULES enabled by the emulator. This shows GPP predicted by the emulator for a single location in 2002. The gray lines show all possible predictions of GPP, and the black lines are observations with some uncertainty bounds. We used history matching to gradually rule out combinations of parameters that gave quote-unquote bad results. And in the end, we have parameter values for JULES that give realistic results for this set of observations. So in summary, emulators are quick tools for analyzing the consequences of landscape decisions. And we built an emulator and tested several applications with promising results and lots of lessons of how not to do things along the way. It was a short project, so there's a lot of work left to do. We'd like to further develop this methodology to reduce uncertainty in land surface models like JULES. We could easily examine other inputs of JULES, as I mentioned before. And emulators of land surface models could be used to help answer complex questions about landscape decisions. If you want to know more, you can get in touch with me or look out for the paper by Evan Baker, which we hope to submit to geoscientific model development soon. Thanks very much for your attention.